Welcome to the Deep Dive, where we unpack the latest research papers, getting you straight to the core insights. Today, we're diving into something that's been a real headache in AI image editing. Getting the right training data. Finding an input image, the exact text instruction for an edit, and the perfectly edited result. It's a huge bottleneck.
It really is. You can find text and image pairs all over the place, but that specific triplet input instruction output is super rare, especially for complex edits. Building those data sets usually means expensive manual work.
Yeah, and that bottleneck is exactly what researchers from CMU and Adobe tackled in their paper, Learning an Image Editing Model Without Image Editing Pairs. They call the method NP-edit.
And the core idea is pretty radical.
Yeah.
They found a way to train these editing models without needing those matched pairs at all.
Okay, so let's hit the highlights first with our 1-minute summary. If you just need the quick version, here it is. NP-edit's big breakthrough. It completely ditches the need for supervised input instruction output image pairs for training.
How? Well, the mechanism is quite clever. They train a diffusion model, but only for a few steps, and they guide it using differentiable gradient feedback. This feedback comes directly from a vision language model, a VLM. So the VLM acts like the supervisor, even without a ground truth image.
But just following instructions isn't enough. The image needs to look real. Yeah. So the VLM feedback is paired with something called a distribution matching loss, or DMD. Think of it as a guardrail.
Exactly. The DMD makes sure the edited images stay realistic, that they look like natural photos and not weird AI artifacts.
And the result, well, their final NP-edit model, running in just 4 steps and having about 2 billion parameters, performs really well. It's competitive with, and sometimes even better than, much, much larger models that were trained on huge paired data sets, especially in these efficient few-step scenarios.
A big deal for efficiency.
Definitely. Okay, let's dig deeper into that data problem. Why has this been such a persistent issue? You mentioned text-image data is easy. Why is editing data so much harder?
Well, like you said, it's the specificity. You're not just generating an image from text. You're starting with a specific input image and transforming it based on an instruction. That mapping, that transformation learning, is what needs the paired data.
And the old workarounds just haven't cut it.
Not really, no. Especially not for the kind of diverse, high-quality edits people expect now with models like Stable Diffusion or Midjourney as the baseline.
What about trying to generate synthetic pairs? Like using one model to create edits for another model to learn from. Destruct too? Pix tried that, right?
Yeah, and it was a good early step, but it has problems. First, you risk the generator model just passing on its own flaws or biases into the training data. If the base model makes weird hands, your synthetic data might teach the editing model to make weird hands too.
Propagating errors.
Exactly. And second, that synthetic data gets stale fast. As the base text-to-image models get better, the data generated by older models just isn't good enough anymore. You're constantly chasing the state of the art.
Okay, so synthetic data is tricky. What about pulling frames from videos? Couldn't that give you before and after shots?
You'd think so. And sometimes they can work for very simple things. But videos mostly show smooth, continuous changes, someone walking, a car driving.
Right.
They rarely capture the kind of big, discrete, imaginative edits users want. Turn this dog into a cat or make this sunny beach look like a stormy night. Plus, getting perfect pixel alignment between frames showing a significant change is actually quite difficult.
So the common workarounds are flawed. This really sets the stage for NP-edit's approach. They basically said, okay, if we can't get human-labeled pairs, let's use AI intelligence itself as the supervisor.
Precisely. That's the core insight. Use a VLM, which is already good at understanding both images and text to check if the edit instruction was followed. But the real novelty isn't just using a VLM as a judge, like in some reinforcement learning setups.
Right, they do something different.
Yeah, instead of just getting a simple good or bad score from the VLM, they extract dense, differentiable feedback. Essentially, they get gradients from the VLM that tell the editing model how to improve, not just if it needs to improve. And they distill this directly into the generative model.
And this avoids needing that initial supervised fine-tuning, the SFT step, that a lot of RL approaches need.
Exactly. Many VLM-based RL methods still need some paired data to get the model reasonably good before the RL can effectively guide it with scalar rewards. NP-edit skips that entirely. No paired data needed, not even for initialization.
That's a significant departure. Okay, let's get into the weeds a bit. The architecture. They start with a pre-trained text-to-image model, let's call it GIT, and fine-tune it into their editor, the Layla. How does it take the original image into account?
They use a pretty standard technique, concatenation. They encode the reference image using its VAE encoder, and then they basically just stick that encoding into the sequence of tokens that the diffusion model processes, along with the text instructions encoding.
So the model sees the text prompt and the visual information from the input image side by side.
Yeah, the attention layers can then figure out how to relate the instruction to the specific parts of the reference image it needs to edit.
Okay, now the training magic. Standard diffusion training needs the final, clean target image, $6 to calculate the noise it needs to predict. But here, there is no ground truth, $6. How do they get around that?
They use this technique called unrolling the diffusion trajectory. It's a bit complex, but the idea is instead of comparing to a real clean image, they simulate the denoising process during training.
How does that work, roughly?
The model starts with noise, makes a prediction of the clean image after one step, then it takes an intermediate noisy version of that prediction and refines it in a second step. They actually use 4 steps in the final model. This process generates a sort of high-quality target on the fly.
And doing it in just a few steps, like 4, is really important, isn't it, because of the VLM?
Absolutely critical. VLMs are amazing, but they aren't perfect. They really struggle to make sense of very noisy or blurry images. If you're trying to use VLM feedback early in a standard 50-step diffusion process, the VLM's judgments would likely be unreliable.
Ah, I see. So by keeping it to just a few steps, the images being judged by the VLM are already reasonably clear and structured.
Exactly. Clear enough for the VLM to give meaningful feedback on whether the instruction was followed.
Which brings us neatly to the dual loss system. This seems to be the heart of NP-edit. 2 losses tackling 2 different problems. First, the VLM-based loss, level MLer for instruction following.
Right. Think of LVLs as the instruction checker. They have a set of question templates, maybe around 10 categories like add, remove, change style, etc. For a given edit, they feed the generated image and the instruction to the VLM. They used a level 1 of Vision 7b and ask it specific questions.
And the VLM answers yes or no.
Basically, yes. They optimize the loss based on the VLM's internal confidence scores, the logits, for the yes versus no tokens. But crucially, it's not just one question.
Oh, what do they ask?
For each edit, they ask 2 key things. First, the edit verification question. Essentially, did you perform this requested edit? Like, is the chair blue now? Second, the identity preservation question. Did you mess up the rest of the image, or does it still look like the original input, just with the edit?
That second question sounds vital. Otherwise, the model could just ignore the input image and generate a totally new one that follows the text prompt.
Precisely. It keeps the edit grounded in the original context. Without it, you lose the editing aspect.
Okay, so LVLM handles making sure the instruction is followed correctly. But then there's the second problem, making sure the output looks real. Why wasn't the VLM enough for that?
This is a really important point the paper makes. While VLMs are great at understanding concepts and following instructions, they are not reliable judges of photorealism or overall image quality. They can confirm an edit happened, but they might say yes, even if the result looks like a weird, glitchy mess.
So relying only on LVLM would give you compliant but potentially ugly images.
Exactly. The ablations show this clearly. Training only with UCLM leads to unrealistic outputs, artifacts, and eventually the training just falls apart.
So that's where the distribution matching loss, the DMD, comes in. It's the realism police.
That's a good way to put it. DMD works by comparing the distribution of images generated by the fine-tuned editor to the distribution of images generated by the original, powerful, pre-trained model. It minimizes the difference, essentially forcing the editor's outputs to stay on the manifold of natural-looking images.
It's learning to look like the kind of high-quality images the original teacher model could produce.
Exactly. It keeps the outputs visually plausible and prevents the VLM loss from pushing the model into weird territory just to satisfy the instruction.
Got it. And quickly, the training recipe, they didn't just throw both losses in from the start.
No, they have a brief warm-up phase first. They train the model for a short time just using an identity loss, basically asking it to reconstruct the input image. This seems to help stabilize things before they introduce the main VLM and DMD losses.
Makes sense. And then the final loss is a weighted sum.
Yep. They found evolVLN needed a pretty small weight, like 0.01, while LDMD got a much higher weight, 0.5. It suggests you need a strong push towards realism, DMD, and a gentler nudge for instruction following VLM.
Okay, let's talk results. How did NP-edit actually perform? They used GetItBench, measuring VIE score, which combines semantic consistency, SC, did it follow the instruction, and perceptual quality, PQ, does it look real?
The results, especially in the few-step setting, are quite impressive. Remember, NP-edit is a 2 billion parameter model running in just 4 steps. In that setup, it got an overall VIE score of 6.9. But the really interesting part was the perceptual quality score.
How did it do there?
It scored 7.69 on PQ. To give you some context, QuintImageEdit, a much larger 20 billion parameter model, only scored 6.21 on PQ when run in 4 steps.
Wow, so NP-edit produced images rated as significantly more realistic, using way fewer parameters and the same number of fast steps.
Exactly. That's a major win for efficiency. The paper shows examples like changing a sheep's color, where NP-edit's result looks natural, while other methods sometimes make the edit look flat or obviously stuck on.
And this wasn't just for simple edits, right? It worked for more complex, free-form stuff, too.
Yeah, they tested it on tasks like customization, where you take a specific object from a reference image, like a particular backpack, and generate it in a totally new scene described by text, say, in a forest clearing.
Like Dream Booth-style tasks.
Sorta, yeah. And even there, NP-edit, again using fewer parameters and far fewer diffusion steps, maybe 8 steps compared to 28 or 50, for others achieved comparable results. It did a good job of keeping the specific object's identity while placing it convincingly in the new context.
The ablation studies really drive home why the whole system works. What happened when they tried removing parts, like training only with the DMD loss?
If you only use DMD, the model gets good at making realistic images, sure, but it struggles with the actual editing instructions, especially harder ones like removing an object cleanly. The semantic consistency score dropped quite a bit, down to 4.93. So, looks real, but doesn't do what you asked.
Okay, and the opposite. Only the VLM loss. La VLMs.
That was not good. As we discussed, the VLM isn't a good judge of realism, so the outputs became unrealistic, low quality, and worse, the training actually diverged, so it became unstable. The overall score cratered to 1.93.
Yikes. So you absolutely need both. The VLM for the what and the DMD for the how it looks.
Precisely. They're completely complementary. They also showed that things like using their specific binary cross-entropy loss formulation and including that identity preservation question both help performance significantly.
And did performance scale as you'd expect, with more data or better models?
It did. They tested scaling up the dataset size, up to 3 million unique images, and saw performance improve. And using a stronger VLM backbone like InternVL14b instead of InternVL2b also boosted the results. Pretty standard scaling behavior, which is encouraging.
What about comparing this gradient feedback approach to reinforcement learning methods that also use VLMs?
That's a really interesting comparison they included. RL methods typically use the VLM to provide a single scalar reward, just a number indicating how good the edit was. But that sparse signal often isn't enough to train a model from scratch.
Right, you mentioned they often need that initial SFT phase with paired data.
Exactly. RL, like the FlowGRPO method they compared against, usually relies on having a decent starting point from SFT. NP-edit, using the differentiable VLM feedback, gets much richer, denser information about how to improve at every step.
So the gradient tells the model which direction to go, not just whether it succeeded or failed.
Yeah, think of it that way. And the results showed this advantage clearly. NP-edit, starting with no SFT, scored 6.9 overall. The comparison model trained only with SFT scored 3.64, and even adding RL on top of SFT only got it to 4.19.
So the differentiable feedback approach was significantly better, even using the same VLM as the judge or reward model.
Definitely seems superior for this kind of task, and crucially avoids the need for any initial paired data SFT.
Okay, so wrapping up, what's the big takeaway here? What does NP-edit really mean for the field?
I think the main message is that we might finally have a way to break the dependency on expensive, hard-to-get paired supervision for image editing. NP-edit demonstrates you can synthesize that supervision effectively using VLMs, specifically their gradient feedback, combined with a mechanism to ensure realism.
And this leads to models that are not only effective, but also highly efficient, working well in just a few steps.
That's a key practical benefit, yeah. Few-step generation is much faster for users.
Now, they were upfront about limitations, too. What are the remaining challenges?
Well, one is fine-grained pixel consistency. Because there's no ground truth pixel-level target, the edits, while instruction compliant, might slightly alter the shape or texture of unchanged parts of the image more than you'd ideally want. That identity preservation question helps, but it's not perfect.
Did they try adding other losses to fix that?
They did mention trying LPIPS, a perceptual similarity loss often used for style transfer or reconstruction. It did improve pixel consistency, making things look closer to the original non-edited parts. However, they found it actually hurt the model's ability to follow the edit instructions successfully.
Ah, a trade-off. Better pixel matching, but worse editing.
Seems like it. Finding the right balance there is still future work. And of course, the practical issue. Training requires keeping the large VLM in memory alongside the diffusion model, which mean high VRAM requirements during training.
Okay, makes sense. So that leads us to our final provocative thought for you, the listener. NP-edit needed that DMD loss because current general-purpose VLMs aren't quite up to the task of judging subtle photorealism reliably.
Right. But what if that changes? What if future research develops VLMs that are specifically trained or engineered to be much more sensitive to pixel-level details, subtle artifacts, and fine-grained visual consistency? Could we reach a point where a sufficiently advanced VLM could provide all the necessary feedback both for instruction following and for photorealism and identity preservation, making the separate distribution matching loss unnecessary? Could a VLM become the sole supervisor?